we've been getting a lot of requests to do a video on the Nissan SR20 engine. The SR20 engine is one of our favorite engines. In fact, the principals here, me, Jeff, and Martin, all met each other over our love of the SR20. So that's a kind of an interesting story. But we have fond feelings for the SR20. And we have a basic SR20 build here. It's going to go into one of our buddies' kind of play around drift car. It's not like a totally killer build, but we can do those. We can do one of those later. But you know, it's a nice basic build. Can hold up to the rigors of like amateur drifting, and it's a perfectly good street motor too. So if you like this content, mash that subscribe button. It helps us out. Comment, we'll try to do some answers to your comments, and go to MotoIQ.com and check out our articles. We got tons of SR20 content there. So with that being said, let's get on to the engine. The SR20 is a pretty strong engine. It's a closed deck. It's all aluminum. It's pretty light. It has a really strong bottom end. It does have some limitations though. When we're going through the SR, the first thing we want to do is change the pistons and rods. Now the stock pistons and rods in the SR are pretty darn strong, but on the boosted motor, especially one that's going to be drifted, you're going to need something better. One of our favorite pistons to use on an SR is the JE shelf piston. Now when I say shelf piston, this is an in-stock piston that's sitting on the shelf that you can just order. Not custom, but ready-made. The JE piston is made on the FSR forging. Now I really like this forging. It has all the advantages of a strut piston, but none of the disadvantages. It has some of the things that a full-face piston has, but a lot of the lightness of a strut piston. Let me talk about that here. When you look at it, you can see on the thrust side, it has a full face. The thrust side is the side that gets pushed into the cylinder wall, so you want to have a lot of bearing area. You can see that it has a full contact patch, wide bearing area, but on the non-thrust side, you can see it's like cut down like a typical racing strut piston. So it's narrow, lightweight, and low friction. The FSR piston also, you know, normally has reinforcements and buttresses, but on the small bore diameter like the SR20, it doesn't really need to. But you can see that the piston boss is like really integrated into the design and is really out close to the edge of the piston's periphery. So the pin boss area is nice and strong. Another cool thing about the FSR is that it uses a near net shape forging. So what that means is the forging blank is actually really close to the size of the actual finished piston. So that means there's not like a lot of excess undercrown material. The crown is just the right thickness it needs to be, and the skirts have to be are right there too. So you don't have to have a lot of like excessive milling, but the piston's still nice and light. The other advantage of the near net shape forging is that the grain flow and everything is not like compromised too much. A lot of piston companies just use like a big old cylindrical billet and cut the piston out of that. But what JE does is their forging die is really close to the shape of the piston. So that means you get good grain flow around the skirt, good grain flow around the pin boss, and good grain flow under the dome. The grain of metal is kind of like the grain on wood. So if you messed around with wood, you know that if you go against the grain and put some force, the wood snaps. But if you go with the grain, the wood's really flexible. Same goes for metal. With a near net shape forging, the grain is going in all the right directions of the piston. Some of the other features of the JE piston are a pressure equalization groove between the number 1 and number 2 ring. This helps as a pressure reservoir to make sure that you get pressure in back of the number 2 ring to improve sealing. It's kind of an advanced feature that has come into vogue in the past few years. A lot of Pistons still don't have it. Other things are the ring set is a pretty advanced ring set. They're all like thin, low tension for minimal drag and minimal inertia, so you're not likely to get ring flutter. The number 1 ring is nitrided steel. The nitride facing is really hard and wear resistant, and the steel is resilient, thin, and conforms to the bore real well. The number 2 ring is a ductile iron. It has a Napier profile. A Napier profile has a little hook on it. This hook beds in really quickly and helps contribute to a good seal of combustion pressure. The hook profile does it. It's a little cool thing. Works really good as a number 2 ring. The oil ring is super low tension, thin, and really low drag and really effective. It has like a lot of drain back holes to the interior of the piston, and it also scrapes up oil off the cylinder walls to feed to the piston pin via oil holes. This is kind of important for a turbo motor, keeps the pin area lubricated. Some of the other features too are a polymer coating on the skirt. You can see it here. These little areas where the polymer isn't there, that's the measuring pad. So when you set your piston to wall clearance, you're not measuring the coating. Overall, we're really impressed with this piston. I mean, shoot, you can't get much better than this, especially considering it's a shelf piston. For this particular engine, we're using an Eagle connecting rod. An Eagle rod is a fairly inexpensive rod that's actually really high quality. I mean, we've used these for years. We've even used them in racing engines. We've never had a single failure. We've never had one of these not measure out well, so the machining's always been good. The Eagle rod is made out of a 4340 alloy. 4340 is like a chrome moly, but it has extra nickel that makes it like really tough and ductile. Exactly what you need in a connecting rod. The Eagle rod is also made on a near net shaped forging. A lot of rods are just cut out of a forged billet, so the grain's only going in one direction. The Eagle's actually made on a forging that is shaped like a rod, and then they do the final machining. This means that the grain is going around the big end of the rod like a circle, so you don't have any straight grains, so that really helps the toughness. There's some other features like there's dual pin oiling holes like on the underneath of the rod. A lot of rods have the pin oiling hole at the top, but that's also the highest stress part of the rod, and you don't really want a hole there if you can help it. So what Eagle does is put 2 small holes underneath, and that way you don't have that stress place up on top of the piston. I mean, I think that's really cool. There's like an extra rib down here in the groove. Like doing some computer analysis, Eagle found that adding this rib really increased their fatigue strength without adding much weight. The Eagle rod is double shot peen, so it's shot peen with a big shot first to get a compressed layer in there really good, and then with a smaller shot to like really refine the grain on the top skin. Now, shot peening is bombarding the metal with a spherical hardened steel balls, and this kind of like microforges and puts a tough skin on the outside of the part. So you get grain refinement, it shrinks the grain, it toughens it up, and makes like a really tough skin that cracks have a hard time propagating in. When you do shot peening, it improves the fatigue strength of the part at least 100%. And in a specialized type of shot peening like what Eagle uses, It's probably closer to 150%. Eagle uses ARP 2000 rod bolts, which are kind of like the industry standard. Really high tensile strength. You can also see that additional reinforcing rib at the bottom of the rod cap. Overall, it's a great rod for the price, and we don't hesitate to use them. Another good rod that you might want to use is K1. It's about the same, in the same price range, has the same features, same material, sits on the shelf, it's in stock. It's also a good cheap rod. This just happens to be an Eagle rod, but we like K1 too for this sort of price point of an engine. So that's our piston, rings, and rods. For bearings, there's a number of good bearings on the market, but we really prefer the King XPC bearing. The King bearing, in my opinion anyway, it's probably the highest load bearing capacity bearing on the market. It's a tri-metal bearing with a steel backing with an overlay of lead, tin, copper. That alloy is really tough, and it really can hold a lot of load. Now it's a racing bearing, so it's not gushy and it can't embed a lot of dirt like a stock bearing, but that's the drawback. What really sets the XPC apart is it has a coating. Now it's not just a regular coating like a typical bearing, but it's a polymer and it's filled with copper nanoparticles. So the copper nanoparticles are actually pretty hard. They give the coating some body, and it actually increases the load bearing capacity of the bearing by about 15%. Your typical polymer coatings that are found on some bearings are more like a dry film lubricant, and they help the engine on break-in, and they help a little bit if the crank touches down, like if you have a fluctuation in oil pressure. I mean, it helps, but it's not actually increasing the load bearing capacity of the bearing. So the King coating actually does all that, plus helps the load bearing capacity, so you can't beat it. It's one of our favorite bearings. One of the sometimes problems you have with the SR20 is it has a really small oil pan, and it doesn't have much baffling. So you're prone to starvation in the corners. Also, you're prone to being really sensitive to oil level. You have just a little too much oil in the crankcase, you get a lot of windage, and your oil temperature shoots up and your oil gets all aerated, and you start losing some of your protection for your bearings. So in this case, where you're running like an Injiku oil pan that goes, replaces that little bottom part of the stock oil pan. This gives about another half quart of capacity. Now maybe it's about 3/4 of a quart, and it has trap doors around the baffles. These trap doors help keep the oil around the pickup even when cornering. This is a nice part. It doesn't really cost that much. It's a great deal. There's other parts on the market, but they're much more expensive, and they more or less do the same thing. So Injiku is really good for the money. So one of the things I don't have on the table that's really important if you're building an SR20 is an underdrive water pump pulley. Now the stock SR20 pump starts to cavitate at about 6,500 RPM, and it's in full cavitation probably by 7. So when it cavitates, the pump impeller is spinning around and it starts to make bubbles. And when you're in full cavitation, it's just like churning a foam. This means coolant's not going around your motor, which makes the SR20 really prone to overheat. So it's really important to slow down that water pump, get out of the cavitation zone. This really helps prevent a lot of problems. The next thing we're going to talk about is the cylinder head. So this is kind of an economy build, so we didn't put a whole bunch into the performance side of this head. It was mostly to rebuild a head that's seen a lot of better days. Now this engine has been put through a lot of drifting, a lot of drift days, a lot of pounding on the street. The head was pretty messed up. So what we did is we wanted to cut the seats oversized so we could have a nice new valve seating surface, set the valves up nice and high so they would flow really well. So we went to SuperTech oversized valves. Now these valves are 1 millimeter oversized from stock. The exhaust valve is Inconel, which is a super high heat resistant alloy, really important to use on turbo engines. The intake is a stainless that's black nitride. Nitriding is a really hard, slippery, heat resistant surface treatment. So that really helps the wear and longevity of the valve. When you look at the SuperTech valves, you can see that they have a reduced stem diameter in the area right under the head. Now, this actually helps flow quite a bit. I don't have the exact flow numbers on an SR20, but typically it's between 5 and 10% of the overall flow across the board that you can pick up by reducing the diameter. Seems crazy, but I've seen data on other engines. Another cool thing is the intake valve is kind of a flat nail head contour. Now, this kind of contour in the intake generally helps low lift flow. Low lift flow is the most important because your valves spend twice the amount of time at low lift as they do as high lifts. So, you know, we do a lot of little tweaks to help the low lift flow, and generally that helps power and torque, and it doesn't have any negative characteristics. So the exhaust valve has kind of what we call a tulip contour. As you can see here, it's kind of more conical. So when your intake valve is flat, that helps your intake flow. When your exhaust valve is tulip, that helps the flow coming out of the cylinder make the turn to the exhaust port. So that's some features that these valves have that you wouldn't find in your stock valve. Another interesting feature is that the SuperTech valves, the 45 is just the width you need, more or less. You probably heard of a trick with stock valves, putting a 30-degree back cut on the valves to kind of help the flow. Well, in a SuperTech valve, that's already done for you in the contour of the valve. So it has all the tricks to try to gain the flow, especially at low lifts. When you look at what we did to the head, the first thing we did is we opened up the seats for that 1 millimeter bigger valve. So that got us into nice clean material. The old seats were all pitted and the valves were all sunk. That's really bad for flow. But now with the 1 millimeter bigger valve, we're able to seat the valve nice and high, just like a new head without having to change the seats. We also have like a bigger area for more flow. So the valve seats are actually opened up and they're bigger. Like a lot of our motors, we used a Newen CNC machine to cut the seats. So what that does is it cuts a smooth radius from the combustion chamber, then it cuts a nice 45 seat, nice and precisely where it has to be, and then it does a smooth radius going into the ports. Now the traditional way is to do a 3-angle valve job where you have a 30-degree top cut, your 45, and your 70 throat. This is a pretty good way to get performance because it eases the air onto the 45. But when you have a smooth radius with no steps, that works even better. It's one of the reasons why we like the Newen machine. The other thing we like about the Newen machines is it can extend the 70-degree cut all the way into the bowl of the port. So we're actually opening up the whole bowl area so it flows better. We did a couple other things too. We relieved the combustion chamber a little bit where the edge of the valve comes close to the edge of the combustion chamber. This is to, you call this unshrouding. So it gives a little bit more room. So when the valve's first opening, The chamber's kind of laid back, so it doesn't interfere with the flow. And we also like kind of hand touched the last cut that the Newen machine made. So we kind of hand touched and hand blended it into the bowl. One of the things about the SR20 intake port on these high port motors is they have a funky entrance into the bowl, so they have a really sharp edge, like right on the inside. Now that really messes up flow. So what we did is we broke the edge with a die grinder. This actually makes a really big difference on these old high ports, and it's super easy. Like, you don't go to town and take a whole bunch of material out, because that'll make it even worse, but we just broke that sharp edge. Now, when you compare an SR20 to a K motor, I mean, it flows way less than a K motor, and that's why maybe these things naturally aspirated don't make the killer power. Now, the intake port also has some weird things, like there's a hydraulic lash adjuster for the rocker arm, and it sits right in the middle where the port wants to go. So Nissan kind of made this port that's kind of bow-legged to go around that hydraulic lash adjuster, and that kind of messes up the flow. The port has a nice straight shot in, but the port splitter is huge, and that causes a lot of skin frictional losses. So the intake port doesn't flow that great. What's interesting is there's a low port version of this motor that kind of has like kind of crappy angles into the combustion chamber, but because it doesn't have to bend around the lifter and have that long bow-legged port, it actually makes about the same power as these high ports. And the best flowing ones are the SR20VEs, but we'll talk about that in some other video. So we also broke the edge on the short side radius of the exhaust port. This always picks up flow for very little effort. We changed the valve guides to Supertech silicon bronze valve guides. Silicon bronze is a great material. It's strong, it's lubricious. You can run tight clearances without worrying about sticking the guide, and it wears for a really long time. The SR20, being a rocker arm motor, eats its guides, so most SR20s that have any kind of miles on them usually have worn out guides. The rocker arm means that the rocker arm works directly on the valve stem, so it's putting back and forth side load on the valve. It's one of the reasons why the guides go out. You have a motor with a shim and bucket valve train. The bucket takes up a lot of side load, and the valve guides stay good for a long time, but the SR20 isn't one of those. So almost every SR we see needs to get valve guides. This one is no exception. But overall, this is a nice head. I think the stuff we did will pick up a lot of power, and doesn't really cost that much, and it's not a whole lot of extra work on our part. We were probably gaining a lot of the performance of a fully ported head with just a fraction of the effort and cost. So good solid work. This thing should run good. So now we're going to talk about what is the Achilles heel of the SR20 engine, the Valvetrain. Now, if you guys have raced these, drifted them, or even flogged them on the street, you know what happens if you bang the rev limiter too hard in one of these engines. I mean, we've probably all experienced it. The rocker arms fly out and get mashed up by the cams maybe, or if you're lucky, they just fly out and lie there. And the little valve shims go flying, and if you're lucky, you can recover them like up on top of the engine, but if you're unlucky, they get into the pan, and then it's a big pain in the ass. Now, yeah, I mean, if you're an SR20 guy, probably all of you have experienced it. But we have some tips about that. One of the tips is to always use good Valvetrain components. Now, we're all using everything from Jim Wolf technology. There's some details about that we'll get into. Another thing is a trick that we do. You'll probably notice that there's one guide shim, and then there's one flat shim on the other side. The guide shim goes into these guide shoes that sit on top of the valve, while the other side goes to the flat shim, which is a select fit shim where you can adjust your the thickness of the top of the valve. So you have like a whole bunch of these you get from Nissan, and you get the right one that works. So what you do is you put your guide shim in, your retainer, and then you get your select fit one, and then you get a dial indicator and go back and forth, and you get select fit shims, you trade them out till you get it so it's the exact right size. Now, and the tip heights are the same. Now on the SR20, this is super important. Now I know a lot of you guys have blown off your rockers and just thrown everything together, and maybe it's ran pretty good for a while, but sometimes maybe not. One of those things is if you get your shims mixed up, then your rocker ends up being tilted a few thousandths. What this does is it wears your cam lobe out real fast, and it also puts like a thrust load on the rocker, so it makes it so it's more likely to fly out again. Now, I mean, I've been at a race where I kicked a rocker and even broke a couple, and I just dug in my toolbox, pulled up some parts, and put it back together, and the engine ran the whole weekend. And maybe I was lazy, and sometimes it ran the whole season. But I've seen some of my friends that throw off a rocker, throw off another one, throw off another one, throw off another one. And that's when they get unlucky, where their lash up of parts got the rocker tilted and caused it to spit apart all the time. So one of our tricks is, what we do is we grind the tip of the rocker so both sides are narrow, and we use a guide shim on both sides of the rocker. So that way the rocker has two tracks, and it's supported, so it has a double the hard time to get kicked sideways. And then what we do is we get a surface plate with some wet dry paper, and then we kind of sand these guys so we get the tip heights perfect. It's a little bit tedious, but it just about guarantees that your rocker won't fly out unless you do some really crazy valve float or something. One thing, do not do this no matter what the JDM fanboys say, and a lot of you guys are going to flame me, but do not use those rocker blockers. Rocker blockers are really popular in Japan. They're these steel clips that bolt on your cam caps, and they actually have like a little steel tip that holds this on top of your, holds this end of the rocker firmly on the hydraulic lash adjuster. Now, I found that this does almost nothing to prevent the rockers from skidding sideways. Like, it doesn't even seem to help. And what it does is, when you do spit a rocker, instead of flying off and then lying there not doing anything, the rocker will be skidded sideways, and then the cam lobe comes and hammers. It usually breaks this, breaks the rocker arm, and then the broken rocker arm flails around and usually knocks the keepers out of your retainer, and you drop a valve, bends the valve over, creates like total carnage. Most of you guys that drift or do whatever, most of the time, you find all the parts and just put it back together, no problem. Use rocker blockers, usually makes a big mess, and you got an expensive repair bill. Another good thing to prevent valve train problems is to use a really well-engineered set of cams. Now for the SR20 engine, my favorite cams are made by Jim Wolf Technology. A lot of it is because they do a lot of engineering on their cams themselves. So they do kinematic analysis, so they could actually design the cam lobes to stay away from frequencies that causes valve surge or spring surge. Spring surge is kind of the engineering term for valve float. So what happens is, here's your spring. It's going up and down at some repetitive motion, and you get a harmonic in the spring, and the spring can actually get out of sync of the motion. So if you go on YouTube and you search spring surge, there's some really cool stroboscopic videos of what's going on. When you see it, it's gnarly. I mean, like the spring is floating in space and nothing's even touching. So Jim Wolf, like they designed their cam contours to try to stay away from those frequencies. They're like 4th and 5th order harmonics if you're an engineer. They also designed their valve springs so the springs have less tendency to surge in the harmonic range of the cams. So their springs and their cams are paired together. Now, like in my other engine videos, you always hear me preach about using the same springs that the cam manufacturer recommends. A lot of this is that frequency matching, and that's the reason why you do that. But the Jim Wolf springs are designed around the contour of their cams and to stay away from spring surge. The Jim Wolf springs are also super high quality. They're made out of what you call Kobe steel. This is a Japanese spring steel. It's vacuum degassed, which means when it's all molten, they put it in the vacuum, and that any kind of bubbles or anything like that could cause a defect inside the spring and cause it to fail, get more or less sucked out. Super high quality steel. It's really pure, so it's not going to have inclusions in it that could cause the spring to fail. It also has the proper heat treat, and it's shot peen. So same kind of springs that NASCAR, F1, and all the other cool guys use. And you can buy it. It's way better than your typical aftermarket whatever spring. For this engine, I'm using Jim Wolf Technology C1 cam. This is a small turbo, mild build, quick response. I feel the C1 is the ultimate cam for this kind of thing. It has really good specs. Because of Jim Wolf's engineering, they're able to get like the most area under the curve for its class of duration. So these cams have 264 degrees duration, but they have a whopping 476 lift, which is, a lot for an SR. They require the valve springs, but these cams have a nice broad power band. They're not too big for a small turbo, and the valve springs give it a pretty good surge margin for drifting. These cams are also the ultimate full bolt-on cam if you have like a front-wheel drive naturally aspirated SR, like all you guys with Sentra SERs and stuff. So if you have an intake, header, and some tuning, these are the ultimate full bolt-on cams for you guys too. We're also using Jim Wolf Technology's adjustable timing gears. Now these use a combination of different holes and skipping different teeth, but they're all marked. You can adjust these in 2.5 degree increments, which isn't like infinitely variable like some of those Allen bolt ones. But what's good about the Jim Wolf gears is they'll never vibrate loose, and you'll never skip timing like that. They're also simple, and they're also really inexpensive. So for engines that I kind of know what kind of settings that I might do on the cams, I actually prefer these Jim Wolf ones. What I'm probably going to do is I'm going to run the lobe centers a little bit tighter on this engine, so it'll pick up some mid-range, really nice for drifting. So I'll probably advance the intake a little bit and retard the exhaust a little bit. So now we can move on to the bottom end. The bottom end of the SR20 is pretty strong. The stock crank is pretty strong. It can take a lot of power. Most of the older SR20s have this bottom end girdle, which really helps strengthen and stiffen up the main caps. You're probably never going to have problems there. We like to use the stock crank a lot, but they are good, inexpensive stroker cranks available. K1 makes one, Eagle makes one. There's nothing wrong with giving these a mild stroke. But there's nothing wrong with the stock crank too. Some of the tricks we do on the bottom end, like right now, I personally don't feel that there's a good stud kit on the market. Now this could change because I've been talking to some manufacturers, but a lot of the common stud kits don't have enough thread engagement, and at the recommended torque, sometimes the threads pull out of the block. Then you got to time stir it or helicoil it. I don't know why that's so. I just think that maybe a lot of the common kits on the market are probably using studs from some other engines, so they don't have proper thread engagement. But I've been talking to some manufacturers about making a SR20 stud kit that's affordable, that is specifically for the SR20. That being said, if you use like the SR20DE T-bolts, they're really strong, and we really haven't had much problem with them. As far as the crank, we use the stock crank. We usually we magnaflux it, micropolish it, and balance it. Now, if you want, we WPC and cryo it too. We always talk about WPC in our engine builds, and we have a video on that. So you can watch our WPC and cryo videos if you want to learn more about those processes. Some of the SR20 block quirks are the block is really prone to distortion from the head bolts, so it's really important to use a torque plate when you're machining an SR20. Like the bore can distort like over 1/1000th, and like that's half your piston to wall clearance that can be in distortion. The other thing is that the transmission could cause the block to distort, so it's usually best to have like a back torque plate and a top torque plate, because the transmission can distort the back cylinder some. So we bore and hone these, and we do our normal honing where we use a diamond hone, like usually as fine as 600, and we plateau hone with a cork bonded stone, so we knock the asperities off. This gives a nice smooth bore finish that's easy on the rings, and it's low friction, but you still have some grooves in there to act as reservoir for the lubricant, so your rings last a long time. It's nice and smooth when you feel it. It's like, like not like your regular honing, I guess, and you can actually almost see your reflection in there, but it's not like super smooth where your rings aren't good to see. We clean up the deck. That's about all we do. It's a closed deck block. It's really strong. You can bore the stock block up to like 87 millimeters. I think that's fine for a naturally aspirated motor, but for a big turbo, you should probably bore it the least amount possible. I know on my personal motors, like I've cracked the cylinder walls when going like much past 550 horsepower, but that was with a 87 millimeter bore. So that's why I don't recommend going really big. If you're going big horsepower, you can sleeve these, but if you sleeve them, you got to make sure and use a top register sleeve, or else you might get some problems. I also feel like most of the time you're better off using the stock torque to yield head bolts. We've talked about why that's studs are a problem sometimes. Basically, your stud doesn't allow the block to grow, and it causes point load on your deck, and you lose head gasket sealing. Use the MLS head gasket, and we try to keep a nice smooth finish on the deck. Generally, it's all pretty normal stuff. On these SR20DETs, they have piston squirters. That kind of helps keep the pistons cooler and less likely to get detonation. Sometimes if you have a naturally aspirated engine that's running really high compression, we might add them to a naturally aspirated motor. It's pretty easy to add it. Another thing that we sometimes do if it's a big boost motor is we kind of do a mod where we cut a groove in the main saddles in the block, and we use the bearings from a GTIR engine, and they have like a bunch of holes on the backside, so you have full 360-degree oil pickup for the rod bearings. You know, like Nissan, the Nissan factory did this on the GTIR motor, which was their biggest power turbo motor from the factory. You know, we've seen it work both ways. We've seen the stock oiling work pretty good, and we've never had a problem with the GTIR oiling on engines that did tend to spin rod bearings. It's an option that we can do. Like a moderate power engine like this, it's probably not worth it, but if you're building something into the 500s, I'd definitely look into that. But overall, you can get pretty decent power without a lot of money on these engines. It's just they have a few quirks. This engine, it's probably going to be like just under 400 horsepower, should run all day, even in a drift car. This engine is pretty moderate in cost, pretty mild. I guess that kind of wraps it up for a basic SR20 build. If you want to stay tuned, we're going to be doing some more exotic ones later. Like we'll probably do a SR20DE, SR20VE hybrid. Put the SR20VE head on the turbo bottom end. You get the good breathing and the variable cam timing with just your regular turbo bottom end. Also want to experiment with using the later S14 style with the variable intake cam on one of these. We'll show you how to do all of that, but that's going to be coming up. But for most of you that have just the basic SR20, this is a good solid place to start that'll serve most of you right. So if you like what we're doing, like I said, hit the subscribe button. Go to MotoIQ.com. Check out our website. We have a lot of SR20 content there. If you want us to build your SR20, go to MotoIQ.com. Go to the garage services link and fill out a request form, and we'll get back to you. So until next time, we'll see you later. Stay tuned for more SR20 content.